Well, hello boys and girls, this is Daniel for Rock the JVM, and in this video I'm going to teach you how to use the Akka Streams Graph DSL, which is often very confusing, especially when you're starting with Akka Streams. As always, I will recommend that you code alongside me in this video. This video will assume that you are comfortable with Scala and you know some Akka Streams basics, although I'm also going to do a small recap at the beginning of this video. And whenever you need to return to the Graph DSL concepts that we're going to show in this video, just return back to it. Obviously, this video will also be available in written form at rockthejvm.com/blog for your added convenience. So this video will attempt to teach you how to use the very compact and oftentimes pretty confusing Akka Streams Graph DSL to give you the ability to write any kind of streaming topologies in your application. Cool, so I'm here in my coding environment, and if you want to code alongside me, add these libraries to build.sbt. So I'm using Akka version 2.6.5 at the moment of this recording, and you will need to add com typesafe Akka, Akka stream, and com typesafe Akka, Akka actor typed optionally. So this particular library is the most important that you will need for this project. I will also add the appropriate code in the description of this video so you don't need to copy this yourself. Good. Now, let me get back to my code. So in this video, I'm going to assume that you know what Akka tries to do with actors and a little bit of Akka streams, at least what a source, flow, and sync will do. To recap, a basic usage of Akka streams is to create some potentially asynchronous components that deal with receiving and or passing of data around in your application and plugging these components together like pipes. So I'm going to use an implicit val system as an actor system. You can also use the Akka actor typed if you like, but the typed actor system will also need a behavior, which we don't really need for this video. So I'm going to use the untyped one. And I'm going to create a few streaming components that I'm going to glue together. So I'm going to create a source as source with a capital S, which you can import by Akka Stream Scala DSL, so source applied to, and you can pass in any iterable. I'm going to pass in a range. I'm going to say 1 to 1000, for example. So this will create a streaming component that will emit all the elements from 1 to 1000 in order. Then I'm going to create a flow, which is a transformer of data. This will receive elements, will transform them inside, and then it will emit their results. So I'm going to use flow int, and I'm going to import flow from Akka Streams Scala DSL. So flow int dot map. And for every element that I'm going to receive, I'm going to simply, for example, multiply it by 2. So this will be a source that emits elements. This is a flow, which is a transformer. So this receives elements, transforms them, and emits their result. So this flow will emit all the numbers from 2 to 2000 in steps of 2. And then finally, we will need a sync, which is a receiver of elements. And I'm going to say val sync as sync. And I'm going to again import Akka Stream Scala DSL sync. And I'm going to say for each, and I'm going to type it with integer to help the compiler. And for every integer that this sync will receive, I'm just going to run this function on every element. So I'm going to simply print them to the console. Now, these three components are individual, but in order to run an actual application, you will need to plug these together like pipes. And we will create what is called a graph as source.viaflow.toSync. And this is a static graph. This is the description of an Akka stream. It's not active yet until we call graph.run in my main method. So I'm going to type in main, hit enter, IntelliJ IDEA will automatically complete this for me, and I'm going to say graph.run. And at this moment, I have a runnable application, and all these elements that will be emitted from the source will be transformed by the flow, and it will will be printed to the console by the sync. So if I right click and run this application, we'll give a couple of seconds for the compiler to run, and notice that we have all the numbers from 2 to 2000 in steps of 2 printed to the console in turn. All right, so these are the very basics of Akka Streams: sources, flows, and sinks, and tying them together in this fashion. Now, enter the Graph DSL. After understanding the basic flow of Akka, with the pun intended, I see lots of people hitting basically a brick wall when they move to the next level of Akka Streams, which is the infamous Graph DSL. It's not an API, but a full-blown DSL because it looks nothing like usual code. Now, I call this Graph DSL a level 2 of Akka Streams because besides the standard source flow sinks, complex applications will need complex data passing architecture. So for example, if you have an email service and you want to reply all, for example, that particular email which goes through your Akka Stream will need to be broadcast, will need to be duplicated to every single recipient, right? So these kinds of broadcasting streaming components are not immediately available in Akka Streams for us to connect like this with the standard API. And so the Graph DSL was invented. So let's do something simple. Assume that you're starting with a source of integers. So we have a source of ints, and then we want to feed them to 2 independent hard computations. And these computations are independent, and we might want to make them asynchronous, but Akka Streams doesn't really care. And then we want to stitch the results in a tuple, and then we want to print the tuples to the console. Now, almost inevitably, most documentation articles that try to solve scenarios like this will give you the whole structure of the code, which is the actual brick wall that people hit against, because the code is very complex and needs to be broken down. Now, the first thing to have in your mind when you want to solve a scenario like this is to know what kind of components you will need for such a job. And for convenience, the visual diagram will look something like this. You have it on the screen. Now, besides sources, sinks, and flows, we can have other components that have either multiple inputs, like a zip towards the right-hand side of the diagram, or multiple outputs, like a broadcast towards the left-hand side of the diagram. And our graph will look something like this picture with the components separated. Now, the most interesting part of the Graph DSL is that this visual representation will be reflected in the code much more than you think. So the visual diagram was step 0. Make a mental diagram of how you want your data to move in your application. Now, step 1 is the frame. So the framing for the Graph DSL will look something like this. I'm going to define a special graph as Graph DSL, which I'm going to import from Scala DSL package, and I'm going to hit create. This is a curried function where the first argument list is now empty. This can also take some arguments that you don't need to care about at the moment. So you will need to say Graph DSL create, and the first argument list is empty, and the second argument list is a function from an implicit builder as a Graph DSL builder of type not used, and I'm going to put in an error sign. So this structure is pretty complex. So you have Graph DSL create, which is the first argument list, and the second argument list is a lambda, which has a builder of type Graph DSL builder typed with a materialized value, which in our case will be not used. If you want to learn more about materialized values, we also have another video where which I named Jedi values in Akka Streams. I'm going to link it in the description. Now, this particular function will take a mutable data structure in the form of a Graph DSL builder typed with a materialized value which we aren't using, and then the body of the function will describe the actual layout of the graph. Now, still in step 1, we need to bring in some very interesting operators that we are going to use later. So I'm going to say import Graph DSL implicits underscore. This is an import that will give us access to some very nice operators. So this is step 1. I want this this particular framing to enter your muscle memory. So if you take my Rock the JVM Akka Streams course, we create lots and lots and lots of these, such that by the end of the course, this particular structure is actually written by itself, so you don't even need to think about it. Now, after we import Graph DSL implicits, we have step number 2, which is to create the building blocks. Now, I'm going to bring the diagram onto the screen again, and notice that we need to create a source. We need to create 2 flows for our independent hard computations. We need to create a sink, and we need to create our special components, the broadcast and the zip. So this is our job for this step. So let me go ahead and create them. So I'm going to write val input as source of 1 to 1000, for example. This is the source of ints, but this source of ints will be wrapped into builder.add. So builder.add source 1 to 1000, and this will give me back a component that I can later stitch together in the style that we're going to see later in step number 3. So this particular structure is very important, builder.add. As I mentioned earlier, the builder is a mutable data structure, so it's worth having these components added to the builder so that the builder can actually instantiate them once you run this graph. So I'm going to create all my components. I'm going to create the val, let's call this incrementer, as my first hard computation. So I'm going to say builder add, and I'm going to create a flow of int dot map, and I'm going to say underscore +1. This is my hard, quote unquote, hard computation 1, but this can be any computation that you like, any kind of flow. This can take whatever amount of time. And I'm also going to create another, I'm going to name this multiplier as builder.add, and I'm going to create another flow of int, and I'm going to map again, and I'm going to, for example, multiply by 10. This is my hard computation number 2. So these flows are at this moment independent. The way that we're going to stitch them together is in step number 3. But first, let's finish creating our building blocks. Then I'm going to create my sink, which I'm going to name output as builder add, and I'm going to add another sink for each print line. So I'm going to say sink for each, but this time I want the sink to be typed with a tuple of int and int, because my zip structure over here will need to tuple the results together. So I'm going to say sink for each of type int of type tuple, and then I'm going to add the print line. Okay, so these are the basic building blocks. The non-basic building blocks, the broadcast and the zip, will be added here. So I'm going to say val broadcast as builder add, and I'm going to add a broadcast. This is very important. Broadcast from Akka Streams Scala DSL. Broadcast of type int. So I'm going to type it with the kind of element that I want to flow through this component. And the broadcast int takes a number as an argument, meaning the number of outputs into this component. So this broadcast will take a single input, the one from the source that I'm gonna stitch together, and then this broadcast will duplicate every single element into both of its outputs. And you can have broadcast with as many outputs as you like. In our case, we're simply going to have 2. And I'm going to also add a zip as builder.add, and I'm going to add a zip component, which I'm going to import from Akka Stream Scala DSL, zip of type int and int. Zip takes 2 type arguments, and the type arguments will also inform the zip component of how many inputs will be added to this component. So zip with int and int naturally takes 2 inputs and a single output of type tuple. So the zip works in the following way. When both the inputs of this zip component have an element ready, then this zip component will fetch an element from the first input, an element from the second input, and it will tuple them together, and it will emit a tuple. All right, so I'm going to use this zip component, and right now we're done with step number 2. So these are the non-standard components. So that was step number 2. Step number 3 is the actual most fun and also the hardest to understand if you've never seen this before. So Step 3, glue the components together. So watch what I'm writing very closely. I'm going to say input feeds into broadcast. When I say feeds into broadcast, this squiggly arrow operator will tell me that the output of the source will be fed into the input of the broadcast. And the squiggly arrow is obviously a method that we're going to use in Fix because it looks cool. And this squiggly arrow will connect these two components together. And the method will also take the implicit builder as argument. And so the builder will also be informed that the layout of the graph includes the connection input to broadcast. All right, so when you say something like this, the builder is automatically informed that you have the connection input to broadcast. Then we can also write broadcast.out at index 0, that is the first output of the broadcast, feeds into the incrementer, which is my hard computation number 1, which also feeds into zip.in0, the first input of the zip. So you can also chain these components together with a squiggly arrow operator. I like to read this as feeds into. So you can read this code as the first output of broadcast feeds into the incrementer, which feeds into zip.in0. And in the same fashion, you can also say broadcast out1 feeds into the other flow multiplier, which also feeds into zip.in1. And finally, we have zip.out, the output of the zip, which is a tuple. Look at that. We have an outlet of tuple int and int. This feeds into the output sync. All right. Now, the code looks red because we haven't returned a value in this whole big function. And this is step number 4. This is the closing. Now, because this particular graph doesn't have any open inputs or outputs after we tied all the components together, we need to return a closed shape. Closed shape is a singleton object, which is a marker for Akka Stream to validate your graph when you instantiate it. So if you have some inputs or outputs left open, if you're mistaken about something, if you haven't tied all the components together and you still declared this graph to have a closed shape, then Akka Streams will throw an exception before this graph is instantiated. All right. So this is a marker for Akka Streams to validate your inputs and outputs. All right. Cool. So this is the structure of a graph DSL. We have graph DSL create with this big ass function, and we broke down the structure of a Akka Stream graph. And finally, after you're done creating this graph, all you have to do is materialize it. So as we wrote earlier, graph.run, we also need to say runnable graph dot from graph, and I'm going to pass in special graph, which is the shape of a graph, which is the description that we described here in this function. And then I'm going to call run. So when you say runnable graph.from graph, you pass in special graph, which is just the description of an Akka Stream. And this description will be passed to the runnable graph.from graph method. And then you'll get something that can actually be materialized. And so you are able to call the run method on it. And before we run this application, let's see how this graph will actually work. So we have the input, which feeds the elements 1 to 1000. And these elements 1 to 1000 will be fed into this broadcast, which will duplicate them into the incrementer and the multiplier independent flows. And so you will have the numbers 2 to 1001 after this flow, and 10 to 10,000 in steps of 10 as described by the other flow. And these two results will be tupled together by the zip, and those tuples will be printed to the console. So if I right click and run this application, we're going to see some tuples printed to the console. So notice that we have the number 210, 320, 430, 540, and so on and so forth, up until 1001 and 10,000 as described by these flows independently. Alright, so I hope this was useful. You can find the links to everything that we discussed in the description attached to this video. Now, if you like it, go ahead and click the like button for me and subscribe, because more videos like this will be coming soon. In the meantime, follow me on Twitter and LinkedIn for updates on upcoming material. And in the meantime, thanks for watching.